today's modern era of rail transport, many different innovations and technologies are needed to carry our passengers and freight, and one of these is railway electrification. In today's video, we will discuss the history and functions of railway electrification and why many railroads use it and adapt it in today's modern era. I am the Transit Diaries, and I like to make videos about urban and transport infrastructure. Enough talk, let's get started with today's video. In general, railway electrification is the use of electricity for propulsion of a rail vehicle. The electricity must be supplied through direct contact with an electricity conduction device and the railway vehicle. The electricity supply that the train takes in comes in many different forms, such as rail-supplied electricity or wire-supplied electricity. Along with this, there are many other complexities, such as the kind of electricity used. The third rail is a method of electricity transfer through a third rail sitting on the side of a rail track or in between the rails. The voltage and electricity type can vary throughout third rails, but third rails are typically used on metro systems or rapid transit. This is due to the large amount of tunnels. Overhead wires simply wouldn't be practical, as metro trains would have to have pantographs installed to them, and you would also have to have higher tunnel clearance to accommodate for electric wires. It's also a much simpler setup, as you don't have to fiddle with any cables, and it's just a rail that you place down on some short stubs, instead of large columns like with overhead wires. The electricity in third rail systems are typically DC current, and typically have their own substations. So how does a train receive power from a third rail? Typically, the bogie, otherwise known as a truck or a wheel set, has a contact shoe that sticks out and makes contact with the third rail. One downside of the third rail system, though, are the safety concerns. The rail remains electrified at all times during transport operations. To combat this safety vulnerability, third rail systems have electric insulation over the top of the third rail, as the contact chute could just hit the third rail from the bottom, so the top is not needed. So in case someone falls on the tracks and decides to sit on the third rail, nothing will happen. Okay, seriously, don't do that. Another way people can be prevented from making contact with the third rail is through platform screen doors, which I made a video about. Check the playlist on this series on my channel page if you would like to find out more. Now, since I talked about safety in the last segment, you might be wondering, how are these trams with third rails in the ground able to run safely? This is because of a new third rail technology called segmented power supply. This third rail tram system allows trams to use third rail so that they don't need to use pantographs or overhead wires. This allows for a more aesthetically pleasing look, as there are no large poles to hold the wires or any wires through the air. This allows the tram to navigate tight areas and seamlessly integrate with the urban environment, as no installation of poles is needed, as mentioned earlier. And the way this all stays safe in terms of electricity is the segmented third rail. Instead of one long electrified rail through a system, the third rails here are put in segments and are locally electrified through a very small power station. The electricity of these separated segments only activates whenever a contact shoe is over them, which means that the third rail is only electrified when it is directly underneath the train, so it's pretty hard to touch that when the train is rolling over the third rail, thus making it extremely safe. Another reason why third rail systems are primarily used by rapid transport and metro systems is simply because the increased amount of friction. An increased amount of friction can sometimes result in more heat, so if high-speed trains would use third rails, they would just burn because of the sheer amount of speed and friction with the rail and the contact shoe. The highest speed a third rail system can handle is 160 kilometers per hour, or 100 miles per hour, before mechanical failures start to occur. But the fastest ever speed set by a third rail train was by a British Rail Class 442 electric multiple unit on the 11th of April 1988. Its speed was recorded at 175 kilometers per hour, or 109 miles per hour. And on the topic of high speed, let's talk about the next method of electrification, which is used by overground heavy rail and for high-speed trains, and that is overhead electrification. Overhead electrification supplies power to the train through overhead lines, which are suspended in the air by poles. Overhead electrification is used in most heavy rail lines around the world that are electrified. The wires are made out of copper and emit electricity through the wires, and the way the train gets energy from these wires is through a device called a pantograph that is raised from the train body and collects electricity and sends it to the train motors. These wires all have different voltages around Europe, which people sometimes say causes compatibility issues between countries in Europe and the different voltages. In Europe alone, there are various different amounts of voltages and the type of electricity used, such as direct and alternate current. But most high-speed lines these days use 25 kilovolt alternating current. The way that many companies, operators in European countries have battled with this compatibility crisis have been through dual-mode locomotives or multiple units. Dual-mode multiple units use two kinds of electricity and are compatible with various kinds, using different pantographs and electrical systems. Another way this can be combated is through diesel locomotives, or diesel-electric locomotives. Essentially, it works with one kind of electricity, but when it's not on that form of electricity and is in a different area, it can just switch to its diesel motor. Because of thermodynamics, the wires sometimes have issues. For instance, cold and heat, expansion and contraction happens, so how do these wires hold up? It's an insanely complex process and would require its own video to explain, but essentially you could combat it with different kinds of copper. Overhead wires also require a pulley system so that the wire can remain perfectly straight no matter through the heat or cold. These pulleys help tension the wire with weights. There have also been combinations of both electric systems I've talked about in this video, and those are the overhead third rails, but those were tested in the early 1900s and aren't used today, due to many different technical issues. Of course, all forms of electricity, like anything else in the world, is also susceptible to some failures and issues. For instance, overhead wires may have issues with hot or cold, or sometimes has issues with the wind when it sways too fast and gets out of the path that it needs to contact with the pantograph. And this is why overhead wires have vehicles to maintain them, called catenary maintenance vehicles. These vehicles typically have the ability to be self-propelled by diesel, so it doesn't have to make contact with the wire that it is maintaining. This also allows the vehicle to perform maintenance when the power is shut off or when there is a power outage. These vehicles can perform many tasks, such as replacing wire, tensioning it, or de-icing wires, because ice and electricity don't really make a good combination. So next time you're riding that train or you see the electrical wires over the train tracks, make sure to not take the immense amount of engineering and effort put in these things for granted. If you would like to learn more about railways and how they work, check out the previous video in my series. Thank you very much for watching. Any feedback to make this series or my content better would be greatly appreciated. I'm the Transit Diaries, and as always, stay tuned for more.